Welcome to another video. So here we are focusing on atomic combinations, right? So in this past paper problem, I just want us to look at this Limpopo problem from 2025. This was a question 2 in this junior exam. So we will be checking this whole question, right? Now, if you look at, it's quite a simple problem statement. You are just told that there are two molecules, carbon dioxide and water, and in those two molecules they are formed through covalent bonding. Remember, covalent bonding is basically where you have two or more atoms, or what you would call elements. They come together to form one molecule, right? For them to form that one molecule, they decide to share either one pair or more pairs of electrons between them, so that they can complete their valence electrons, right? So that those electrons in the outermost shell of any atom. All right, so that's basically what happens during covalent bonding. So you have two atoms, two or more actually, and then they join together to form one molecule, but then they share a pair or more pairs of electrons. So now we're asked to define the term what a covalent bond is. Not covalent bonding, but a covalent bond. So this is a classical definition of what I would, in my advice, say that before you go to an exam, the first thing you do is, after you've done practicing all your calculations and so on, because you would have practiced, you can't go to an exam without practicing, then the day before or 2 days before, preferably 2 days before, what you do is you take out your list of definitions and you memorize them, so that before you go to your paper 1 or paper 2, you have those memorized in your mind. Right, these are easy marks, 2 marks for just a definition, and they account for about 13% of your overall gross marks, right? So out of that 150, you have about 13% if you get all your definitions. Okay, all right, so for a covalent bond, in simple terms, it's just a bond where there's a sharing of at least one pair of electrons between atoms. Okay, that's it, right? And then obviously you have to, that's why I said memorize. You have to write the definitions that are given in your exam guideline, because those ones are the ones that are recognized by teachers and the people that will mark your paper. They are recognized as the true and official definitions. Okay, so use those ones, but for understanding, you must know that a covalent bond, there must be sharing of electrons from or between two atoms. Okay, all right, so let's write it here. So covalent bond is the sharing of electrons between two atoms to form a molecule. So a typical example would be, let's check for carbon dioxide, for instance. So carbon dioxide has two atoms, right? Those atoms are carbon and oxygen, right? That's carbon dioxide for you. There's carbon and then there's oxygen, right? If you go to your periodic table, right? If you go to your periodic table, carbon dioxide has two atoms. It has carbon and there's oxygen. Okay, so now what we normally say is there are valence electrons for each group, right? See these Roman figures here, these Roman numerals. There's 1 or I, it looks like an I, but it's just 1. So this would be 1, that's 2. Then you skip these middle columns. Then you have 3, you have 4, you have 5, you have 6, you have 7, then you have 8. Right, so these numbers represent the valence electrons of each group. So that means for group 1, all these atoms here, or elements, right? Hydrogen, lithium, sodium, and so on, they all have a valency of 1, right? Group 2, all of them, beryllium, magnesium, they only have a valency of 2, and so on and so forth. Okay, so this is how you start with your Lewis diagram as well. I just want to show you how covalent bonding works for now quickly. So you come to carbon. Carbon has 4 valence electrons. Okay, so the way you represent it in a carbon atom, if you remember from your grade 10, you would say 1, 2, 3, and 4, right? That's carbon for you. It has 4. This number that I was writing, it's even given in your periodic table. That Roman figure, it means 4. Okay, that's how Roman numerals work. So as soon as you get to your exam, just label your periodic table like this so that you don't forget. All right, 1 to 8. You skip the middle row, you continue on the other rows. I mean the middle columns, you continue on the other columns with 3, 4, 5, 6 until 8. All right, so this is carbon. It has 4 electrons in its valency, right? Its outer shell has 4 electrons. Okay, let's check oxygen. This is my oxygen. How many does oxygen have? So we'll represent oxygen with crosses, because you can use crosses or dots. So for oxygen, we'll use crosses or X's. All right, oxygen is group 16, and it has 6 valence electrons. Okay, so how do we represent it? Same thing. 1, oh no, not, we'll use a cross. 1, 2, 3, 4, and then we go back again, 5 and 6. Okay, so this is how we create these pairs. First, you fill all sides. Let's go again. You fill all sides, up, right, down, left, or north, east, south, and west, right? And then if there's still more remaining, you start from scratch again. You start adding, like that's what this is our 5, and this is our 6. So in total we have 6 valence electrons, and then of that 6 we have 2 lone pairs. These ones that are in pairs, this and that, those are lone pairs. They are called lone pairs because they are valence electrons and they are coming as a pair. Usually they don't participate in the covalent bonding unless it's dative covalent bonding, right? But in a normal covalent bonding, they don't participate, those lone pairs, right? So that's how you would do it. This is how you would do this whole thing of taking out the electrons in the valence shells. I'm sorry, the valence electrons in the outermost shell of the atoms. All right, so now we'll put it here, and then we have that. All right, so remember, this is CO2. There are 2 oxygen atoms, and then there's only 1 carbon atom. So it's CO2. So how it bonds is this oxygen and another oxygen, of course, will come and share with carbon. Okay, I think let me draw it from scratch because the sharing here is interesting. So now remember, the main aim why these atoms are trying to share is that what they're trying to achieve is a valency of 8. So the octet rule. So what's happening is in their outer shell, they want to maintain 8 electrons. So what that means is, since carbon only has 1, 2, 3, and 4, it needs 4 more electrons so that its outer shell can have 8. Currently, its outer shell only has 4. All right, so coming to oxygen now. Oxygen has 6, which means it needs 2 more so that it has 8. So what does it do? It comes this side. It can only share the ones that are not lone pairs, which is this one and that one. Okay, the lone pairs, not really, unless it's dative covalent bonding, which we can always talk about some other time. But for this example, let's talk about just the normal covalent bonding. Okay, so what will happen is these two, it is willing to share, but it needs 2 more so that it can fill its outer shell, so that its outer shell will have 8. And then this carbon needs 4. So that's why we have 4. We have 2 oxygen atoms. So in these 2 oxygen atoms, let me just use maybe arrows. This one will be coupled with that one. This one will be coupled with that one. Okay, for the first oxygen atom, this atom, electron will be coupled with that one, and that electron will be coupled with that one. Now if you check, what will happen is carbon, our central atom. Why is it our central atom? It's at the center, right? Let's start with the oxygen on the left, right. It's sharing. So for the oxygen on the left, 2, 4, 6. Okay, if we look at it, it has completed its outer shell by just finding 2 more electrons from oxygen. If we count the number of electrons now that oxygen has, it's 1, 2, 3, 4, 5, 6, 7, 8, right? So it has 8 electrons now in its outer shell. Okay, so it's complete now, it's fine, it's happy. But how much does carbon have? Carbon at this point has these ones. It has 1, 2, 3, 4, and then the other 2, which it already had, 5 and 6. So it needs 2 more. So that's where the other oxygen atom comes in here, and then it gives off these 2 single electrons, not the paired ones. The lone pairs, they don't really participate, they just stay there. These are the lone pairs, they just stay there, right? It doesn't matter how you arrange these lone pairs around the oxygen atom. One can be there, the other pair here, doesn't matter, as long as they are the correct number of lone pairs. But now when you check, carbon has 8 now. This is our carbon ring, let's call it carbon ring. So it has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen on the right also has 8, and the oxygen on the left will also now have 8. So they are all happy now. Okay, so this is how covalent bonding works in molecules. Then we would represent this using lines. So we would have the C at the center. If there was 1 electron of carbon being shared with oxygen like that, we would only draw 1 line and do this to represent that bond. But now there are 2. There's 2 electrons from each oxygen and carbon, and that is being shared in between. So we have to use 2 lines, one for the top and one for the bottom. So one for that and the other one for this. So that's why we have 2 lines basically. So the same thing will happen this side, 1, 2, right? So this is how they create those lines that you see in between central atoms and the other atoms that they are bonding to. Okay, so since it's a double bond, it means this bond is stronger than if, let's say, it was something like this, right? Double bonds, triple bonds, and so on are stronger than single bonds. Okay, all right, so that's just a quick refresher on covalent bonding. Okay, so how you would have written it, you're going to say this oxygen plus that oxygen would then give you everything we just got here. Oh, I left out some things. That's our molecule. Okay, so yes, that's what we mean by covalent bonding. And a covalent bond is exactly what's between the carbon and the oxygen. This one would be called a covalent double bond because there are two electron pairs being shared. Okay, so that's why it's a double bond. All right, let's continue. So now we're going to 2.2. One of the above molecules has lone pairs of electrons on the central atom. Again, what is a central atom? It's that atom in the center that holds the other molecule, the other atoms together, right? So for in this case, it will be carbon. Carbon is at the center, right? And these two oxygen atoms are bonding to carbon, right? It's just the molecule, the atom that will be at the center, right? So we are being told that that central atom has lone pairs. So from what we just did here, after bonding, carbon doesn't have any lone pairs remaining. It's just empty here. So it means water has to be the one that has a lone pair, right? We can even plot water. We know that hydrogen has one electron on its outer shell. Oxygen, on the other hand, has 6, but with 2 lone pairs. And then there's hydrogen again. Then this would give us, because this would go there, that would go there, and then we would have something like this. O, and then it's bonding with hydrogen there, bonding with hydrogen there. So you see, the one that has a central atom with lone pairs is water. It even has 2 lone pairs. All right, so we know for sure it has to be water. Explain what is meant by a lone pair. All right, so what's the official definition of a lone pair? Okay, let's put it here. 2. So a lone pair, by official definition, of course, I've already shown you what a lone pair is, just these electrons that won't really participate in the covalent bond, right? But now, how do you define it? So you'd say a lone pair is, it's just a pair of electrons, and then in the valence shell of an atom that is not shared with another atom. Basically, that's how you would say it. So they don't participate during the covalent bond. They are already paired, so they don't really participate. All right, so that's what a lone pair is. So let's write it. Lone pair all right, so that's what it is. A lone pair is just a pair of electrons in the valence shell of an atom, and usually those electrons are not shared with another atom. Okay, so what I've been saying about the oxygen, you see they remain where they are, untouched. Okay, because they can't be shared with the other atom or atoms that oxygen is bonding to. Could be oxygen, it could be any other atom. Okay, all right, so just note these, you can find them. These definitions are on your exam guidelines. Okay, so you don't have to struggle with definitions. They are all on your exam guidelines. Okay. All right, so let's go to 2.2.2. Draw the Lewis structure for this molecule. So they're asking us to draw the Lewis structure for the molecule which its central atom has a lone pair, and we've already done that. So I'll just copy this and then I'll bring it to here, which is 2.2.2. Right, so that's how it is. We would just put it there. Obviously you don't have to shade the lone pairs, just leave it there. Okay, let's make it neater. I don't like it. So we would have our there's our H there. Yes, so that's our Lewis dot diagram. You don't have to draw those smaller Nyana circles. Also, you could have drawn it in a different way. There's no fixed way of doing it. Okay, so even if you did it like this and then you had maybe something like this, your H is here and then your other H is there and then the lone pairs are somewhere here, it doesn't matter as long as there's the correct number of lone pairs, the correct number of atoms, and the structure makes sense. Okay, so if you check this and that, it's the same thing. If you count the number of pairs that are bonding on my first one and the second one, you'll find the same thing. If you count the number of lone pairs, they are the same, but the arrangement is not the same. So don't be worried if perhaps you had done it like this and I come and I do it like this. It's the same thing, right? So just know that. All right, so let's go to 2.2.3. Identify the central atom in this molecule. We have identified it. We said it's just the atom that is in the middle of these two other atoms that it's bonding to. So this would be oxygen, right? The oxygen atom. All right, 2.2.4. How many lone pairs of electrons? Okay, this exam was interesting. So if you didn't know what lone pairs are, you are not going to get this question very well. So we counted how many? 1, 2 lone pairs in oxygen, right? So it has 2. We just write 2 lone pairs. All right, so now what is the molecular shape of this molecule? So this you must know it off by heart. If you check your tables in class and so on, they usually give you this table where you have the ideal shapes and the non-ideal shapes, right? Your bipyramidal, the linear, all those type of shapes, right? So you must know all of that and how each molecule, typically the molecules you would get asked is water, carbon dioxide, and the likes, right? So you must know those molecules in terms of what is their shape. Okay, otherwise you won't be able to answer when you're asked about the shape of the molecule. So for this one, if you remember correctly, even on your diagrams, let's see, 2.2.5. For this one, if you had forgotten, you would remember that if you draw the structure, it looks something like this, right? Oh no, this is carbon dioxide. I want water. It looks something, the usual structure of water. Sorry. is usually something like that. If you remember the structure, you would remember that this is bent, right, or angular. Okay, so typically they either use bent or angular. Okay, so yeah, what happens is the lone pairs, they repel the bonding atoms, right? So instead of the structure being like this, the lone pairs, they deform it by repelling these bonding atoms, and then they end up forming an angle instead of a straight line. So that's why it looks like that. Okay, they just get repelled so that they reach the most stable energy state. Okay, so this is a bent. In fact, I should have brought it here. Bent or angular. Or bent. Okay, that's how you would answer that one. 2.3, H2O can form a dative covalent bond to form the hydronium ion. Alright, so H2O is water, and it can do a dative covalent bond so that it can form hydronium ions. Now use the Lewis electron diagram for water molecule to explain the dative covalent bond. So the way I think about it when I think about dative covalent bond, especially in this example, is you have now a case where the lone pair is participating in the covalent bond, right? But the reason that it's participating is when the bonding atom came, it had nothing to offer, right? So in this case, hydrogen needs 2 electrons to fill its outer shell. That's why here it shared with one other electron that came from oxygen. Hydrogen already had one, it needed another one so that it can have 2 in its outer shell so that it reaches its stable state. And then when it got to oxygen was willing to offer 1 so that they both share that one. But now what happens when hydrogen comes as H plus and it has nothing to share? Remember, since it's H plus, what it means is it has an excess of protons. It has an excess of 1, right? Or it lost 1 electron and now it has more protons than electron, but the difference is just 1, okay, between the protons and electrons. So think of it like this. If hydrogen had, which initially it has just 1 electron, right? Now it loses that 1 electron, right? Its structure now, there's an imbalance. It suddenly has more electrons. It suddenly has more protons, than electrons. That's why we represent it using that sign. So this sign means it has so if you think about it in simple terms, it would mean that hydrogen has 1 proton and then 0 electrons, if you want to think about it like that. Okay, so what happens is now it becomes H plus. So remember, it however needs what? 2 electrons for it to have its outer shell filled. So what do? We bring those 2 electrons. So that's what happens in a dative covalent bond. The hydrogen is coming as an ion like this, and it needs exactly 2, and it's bringing none to the table. Okay, so it can't be sharing, or it can't bring an electron so that the other atom will share with hydrogen, but it comes as it is. So it will come and just take those 2 electrons. Yes, it will still be sharing, but it's not offering something in return. So let me show you what it looks like. So you have, what is it, water, right? Is it 0.6? What is it? Or 2.3.1? All right, so we will start from the structure of water that we had here. This one. Let's remove that. So what happens here? You have this structure of water, and then the hydrogen ion is coming to it, right? It's coming, it wants to bond with this molecule, okay? So it will choose obviously between this lone pair and that lone pair, because it only needs just two electrons in its outer shell. So it won't necessarily take these electrons to itself, but it will come and sit here so that it can share with oxygen. Now it's happy. It has 2 electrons in its outer shell. Okay, so this is how you would draw it. Then you'd have that. And then now, for dative covalent bond, it's important to draw these brackets. Right, so we draw these brackets, and then okay, we'll take this as it is, and then let's put it in here. So this just shows that okay, what happened here is there's the oxygen atom, it bonded with the hydrogen ion, right? And then in it bonding with that hydrogen ion, one of the bonds consists of electrons that were entirely donated by oxygen. So let me repeat that. Then you add a plus here. So the reason we do the square, okay? So this now, everything in the square is what you would call the hydronium ion, H3O plus, H3O plus. Okay, so during the where's my hydrogen here? So when we're doing the Lewis dot diagram, we enclose the final product in brackets and then put a plus outside, right? So what it means is one of the OH bonds, right, consists of electrons that were donated entirely by oxygen, right? So we need to know that. That's why we enclose it in brackets and then we put a plus thing, just to show that. All right, so okay, so and then another way to think about it is, right, so whenever a water molecule, H2O, do you see H2O? Whenever it accepts a hydrogen ion, so that hydrogen ion, remember, it had extra protons. They won't necessarily disappear, right? So even though for this hydrogen ion, it will no longer be H plus, it will just be H, because it will find 2 electrons to fill its outer shell. But now for the water molecule, we will now have an extra proton here, and then this changes to 3. So basically these brackets and then that plus, they are representing this, because if we were writing it only in chemical formula, we would just write H3O plus like this. But now in Lewis dot diagram, we put those brackets and then we write the plus outside the brackets. Okay, it's the same representation as that. Yes, it just shows that the water initially had a balance of protons and electrons, but an extra proton came into the mix, and then now we have H3O and then we have to show that this new molecule will be in excess of 1 proton. Okay, so that's what it means. That's what that whole plus thingy, that's what it means. Okay, all right, so let's close it off with the last one. State 2 conditions for the formation of such a bond. All right, so for the formation of a dative covalent bond, right, because that's what they're referring to. Remove this. So for the formation of a dative covalent bond, you need basically 2 conditions as referred in the question, right? First of all, you need the central atom of one molecule or of one atom. It must have at least one lone pair of electrons available for sharing. So what does that mean? If this oxygen did not have any of these lone pairs, a dative covalent bond was not really going to be possible, because when the hydrogen ion comes, it won't find any electrons to share because they've already been taken by these 2 hydrogen atoms. So that's the first condition, that atom must have at least one lone pair. Okay, the central atom, of course, must have at least one lone pair. All right, so number 2, the receiving atom. Okay, let me just do this. So the receiving atom or ion must have an empty valence orbital. Okay, let's do, so this is my receiving atom. That's what I mean by receiving atom. So this receiving atom or ion, in this case it's just an ion. Okay, so that receiving atom or ion, it must have an empty orbital so that it's capable of accepting the new pair. So if you check hydrogen, we said in its normal state, the one we usually will have one electron in its orbital. Okay, but when it's a plus, it means it has no electron in its orbital, so it must be empty. So it has fulfilled the second condition. First condition, the central atom must have a lone pair. Second condition, the one that is going to bond to that central atom must have an empty valence orbital so that it can accept this lone pair. Okay, so yes, so let's write the answers there. Right, first one, central atom must have at least one lone pair. All right, number 2. So number 1, we said central atom must have at least one lone pair available for sharing. Okay, and then number 2, the receiving atom or ion must have an empty valence shell. All right, so just to reiterate one last time, here's my example. Right, in the example of water, let's see if we can, yes, in the example of water, remember that O is our central atom, right? That's our O. And then these, these are our lone pairs, right? I'll call this one lone pair 1. and this is another lone pair. You must understand these things. When they say lone pair, you shouldn't be lost, okay? So those are our lone pairs, and oxygen is the central atom. All right, so there are 2 lone pairs here, and then the other ones, they are just electrons that are being shared in between these 2 atoms. Or there are 3 atoms in total. Okay, so yes, I think that's it for today's video, and then I'll catch you on the next one. All right.